Hello students, today we are going to start with our chapter of organic chemistry, haloalkanes and haloarenes. This is one of the important chapter of organic chemistry. If I say your 12th class CBSE board syllabus, then your whole organic chemistry carries the weightage of 28 marks. Physical chemistry carries the weightage of 23 marks, and inorganic chemistry carries the weightage of 19 marks. This is what the latest information. If there is any change in this weightage, it will be informed to you later. Now this chapter, haloalkanes and haloarenes, it will include the study of haloalkanes, that means halogen substitutions of alkanes, and haloarenes, that means all the benzene compounds which are halogen substituted on them. So let us first discuss what are haloalkanes. We'll be studying them in detail, and then in haloarenes. Whenever we are studying any chapter of organic chemistry, it has particular sequence. The very first we'll be studying the introduction part. So first we'll study the introduction part. Second, we are going to study the preparation methods. Third, we study physical properties. Whenever we study physical properties, we discuss generally about its water solubility, its density, the trend in melting points and boiling points, etc. We will be studying the nature of the functional group, and lastly, we'll be studying the chemical properties. So you pick up any chapter from organic chemistry, this will be particular sequence, whether I study alcohol, phenol and ethers, whether we discuss about aldehyde, ketones or carboxylic acid, or whether we consider about amines. All the chapters we are going to study in this sequence itself. Now what are the questions related to organic chemistry? There can be plenty of questions which can be given from organic chemistry, like complete the sequence, conversions, which are very easy, but students face little bit difficulty in that. Then word problems, word problems also are there, very easy ones. What happens when type question, then name reactions, give reason questions. Now give reason questions, they are generally based on physical properties. Also complete the reaction, to identify the reagent. These are various types of questions that can be asked from organic chemistry. So we are going to begin with haloalkanes. So I will start with introduction. So what are haloalkanes? Haloalkanes are the substitutions or the derivatives of alkanes in which one hydrogen atom will be replaced by one halogen atom, or I can say its general formula is CnH2n plus 1x. Now the haloalkanes can be classified on the basis of carbon atom to which halogen is attached. It can be either sp3 hybridized carbon and halogen, or sp2 hybridized carbon to which halogen is attached. Now sp3 hybridized to which halogen it is attached, I can say singly bonded carbon atom to which halogen is attached. sp2 hybridized carbon means I can say doubly bonded carbon atom to which halogen is attached. Now this one is further classified into haloalkanes, benzylic halide and allylic halide. Haloalkanes are further classified into 1 degree haloalkane, 2 degree haloalkane or 3 degree haloalkane. Here Rx I have just given a representative of haloalkanes. We can also classify these as monohalides, dihalides, trihalides depending on the number of halogen atom present in them. Benzylic halide. Benzylic halide, it means the halogen will be attached to carbon atom which is attached to the benzene ring. That means the halogen will be attached to the side chain. For example, in this case 1,1-dichlorophenylmethane, halogen atom is attached to the side chain. Allylic halide. Allylic halide means in aliphatic compounds the halogen will be attached. For example, as you can see, prop 1 in chloro, this one is propene, and I will call it as 3-chloro-prop-1-ene. So in allylic halide, halogen will be attached next to the doubly bonded carbon atom. Now this one, halogen atom is attached to sp2 hybridized carbon, vinylic halide and aryl halide. Vinylic halide means halogen is attached directly to the double bonded carbon atom, whereas in aryl halide the halogen atom will be attached directly to benzene ring. Dear students, please pay attention to these two. So many times the students consider these as a aryl halide. This is not a aryl halide, it's a benzylic halide, as the halogen atom will be attached in the side chain, whereas in case of aryl halide the halogen will be attached directly to the benzene ring. Moving on to preparation methods, there are plenty of preparation methods for haloalkanes and haloarenes. First one is from alcohols. It is the most common method, as OH group of alcohols can be easily substituted by halogen. So we'll have plenty of equations in the method of preparation of haloalkanes from alcohols. Then next is from hydrocarbon. From hydrocarbon we have the methods like preparation of haloalkanes from alkane or from alkene. Electrophilic substitution method. This method is generally used for haloarenes. Haloarenes means when the benzene is directly attached to the halogen one. So this we are going to discuss in our next part of the videos. By halogen exchange method, and the last is from silver salt of carboxylic acid. This one is generally used for bromide salts. So we'll begin with the first one, that is from alcohols. So the preparation of haloalkanes from alcohols. As I told you, we have plenty of methods. In that, the very first is any alcohol, if it is treated with hydrogen halide, it will give haloalkane plus H2O. As we can easily see that the OH group gets substituted by halogen, and therefore this OH and H combines and gives water, whereas the remaining part gives us haloalkane. Now if I take any example, let's say the simplest example, ethanol when treated with hydrogen halide gives us chloroethane along with water. Now you can take any other alcohol, simple alcohol, and can carry out its reaction with hydrogen halide. But we have to consider the order of reactivity in this. Order of reactivity means the one which will react faster. 3 degree alcohol react faster than 2 degree alcohol than 1 degree alcohol. This is for alcohols. Whereas if I speak about the hydrogen halides, hydrogen iodide will give reaction faster as compared to HCl, as compared to HBr, as compared to HCl. Now hydrogen iodide, why it will give reaction faster? Because of the difference in the size. Iodine is very bulky in size, hydrogen is small in size, so bond dissociation becomes easier. followed by hydrogen bromide, and followed by hydrogen chloride. Generally, the reactions with fluorine, they are very vigorous, very violent, difficult to control, and therefore they have very limited reactions for the preparation of fluoroalkanes or any other reaction where fluorine is involved. The second method of preparation from alcohols, that whenever any alcohol is treated with hydrogen halide in presence of anhydrous ZnCl2, it will give haloalkane and water. Let us take the example of methanol treated with hydrogen chloride in presence of anhydrous ZnCl2 will give chloromethane with water. Now this hydrogen chloride and anhydrous ZnCl2, it is called as Lucas reagent. This reagent is very useful to us as it is used for distinguishing alcohols. How? That we are going to study in our chapter alcohol, phenol and ether, which is now I am giving you the introduction that HCl and anhydrous ZnCl2, this is known as Lucas reagent, and that test will be known as Lucas test, which we will use to distinguish alcohols. But right now we are focusing how we are going to prepare haloalkane from this. Now this whole reaction is a name reaction and it is called as Groves process. Moving on to the third one. Any alcohol, if is treated with sodium bromide and concentrated H2SO4, then we get specially bromoalkane, sodium hydrogen sulfate and water. But we have to remember that this reaction is applicable to only 1 degree bromide. That means this reaction we can use for the preparation of only 1 degree bromide. 2 degree bromide or 3 degree bromide or iodide cannot be prepared by this method. Why? As you can see, we are using the concentrated H2SO4. Now this concentrated H2SO4, in case of preparation of 2 degree bromide, 3 degree bromide, or even in case of iodide, this concentrated H2SO4 acts as a dehydrating agent. For preparing 2 degree bromide or 3 degree bromide, will require 2 degree alcohol or 3 degree alcohol. So in that case, this concentrated H2SO4 will act as a dehydrating agent, and instead of haloalkane, that is instead of bromoalkane or iodoalkane, we will get alkane. And therefore we cannot use this method for the preparation of 2 degree or 3 degree haloalkanes. The next method involves the treatment with phosphorus halides, either phosphorus trihalide or phosphorus pentahalide. Alcohol, if it is treated with phosphorus trihalide, it will give haloalkane and phosphorus acid. Phosphorus acid we are going to study in detail in chapter P block elements in group 15. Let us take one example. Ethanol, when treated with phosphorus trichloride, will give chloroethane and phosphorus acid. Whereas alcohol, if it is treated with phosphorus pentahalide, we will get haloalkane along with phosphorus oxychloride. And hydrogen halide. So what is the difference between these two methods? The difference is that of balancing and as that of byproduct. When we are using a trihalide, we are getting phosphorus acid as a byproduct, and when we are using pentahalide, we are getting phosphorus oxychloride as a byproduct. The next method is by using thionyl chloride. The treatment of alcohol with thionyl chloride in presence of pyridine will give you chloroalkane along with the byproduct sulfur dioxide and HCl. This is a name reaction called as Darson process. Now you must have seen from this reaction that SO2 and HCl both are gases and therefore they will escape in the atmosphere, giving us pure 1 degree chloroalkane, and therefore it is the best method to prepare chloroalkane from alcohol. Now what is the function of this pyridine? Now when HCl is evolved, there are chances that medium may get acidic. So pyridine neutralizes that HCl and therefore the medium do not turns to be acidic. So I have taken the example of methanol treated with thionyl chloride in presence of pyridine to get chloromethane. The next method from the preparation of alcohol is by using red phosphorus halogen. Halogen can be either chlorine or bromide and we get haloalkane. In all the methods whatever we have studied till now, you must have seen that maximum methods were applicable for either chlorides or bromides. Now suppose we are using 3 degree alcohols. Up till now whatever we have seen, they were 1 degree alcohol. Some reactions are applicable for 2 degree alcohols also. But now if we are taking 3 degree alcohols, then their conditions change. If you want to prepare the chloride, we have to shake 3 degree alcohol with concentrated HCl. If you want bromide from 3 degree alcohol, we have to shake it with 40 to 48% HBr. And suppose we want to convert the 3 degree alcohol to corresponding iodide, we shake it with a mixture of potassium iodide and phosphoric acid. Although these last two methods are not of that importance, but still we have to see it. In all the methods we have seen up till now, remember haloarenes can't be prepared by using alcohol. Anyway, the preparation of haloarene will be discussing in detail in haloarene part. Right now I am just giving you the introduction that haloarenes cannot be prepared by substitution of OH room. So we will move to the next method of the preparation, that is from hydrocarbon. Now when we are studying the preparation of haloalkanes from hydrocarbon, we have two methods, either from alkane or from alkanes. This one you have already studied in your class 11, that whenever any alkane is treated with chlorine in presence of sunlight or ultraviolet light, it gives chloroalkane as the product and it proceeds by free radical mechanism. And therefore you must have studied in your 11th class also that it gives a mixture of products. And hence as such it is not a suitable method for the preparation of haloalkanes. Now when we are discussing the preparation of haloalkanes by using alkenes, there are three different ways. Any symmetrical alkene when treated with hydrogen halide will straight away give haloalkane. But when unsymmetrical alkene is treated with hydrogen halide, there are two conditions, either in presence of peroxide or in absence of peroxide. In absence of peroxide, we know that the reaction takes place according to Markovnikov's rule. And we get 2 degree haloalkane as a major product. In your board exam, you must mention major product and minor product in your answer. You have to specify that. If you don't mention the major or minor product, there are chances that you lose the marks. Now, if the same reaction takes place in presence of peroxide, it is called as peroxide effects, and the reaction takes place against of Markovnikov's rule, that is anti-Markovnikov rule, and we get 1 degree haloalkane as the major product. Also, we have studied that any alkene, when it is treated with bromine in presence of a non-polar solvent like carbon tetrachloride, this bromine gets added across the double bond and we get 1,2-dibromo product, and this is a test for unsaturation. That is, whenever bromine water, brown colored bromine water is passed through alkene, the brown color of bromine disappears as it gets added across the double bond. Now here I want to introduce one more thing, that when halogen atoms are on the adjacent carbon atoms, we call it as a gem dihalide. Sorry, it is a vicinal dihalide. When halogen atoms are present on adjacent carbon atom, we call it as a vicinal dihalide, and when same carbon atom has two halogen atoms, then we call it as a gem dihalide. Understood, dear students? So overall, if I want to say the reaction of chlorine and bromine, I can categorize it in a different way like this, that if any alkene is treated with chlorine or bromine in presence of non-polar solvent, the double bond will be broken and will get vicinal dihalide. If the chlorine or bromine is treated with alkene in presence of HNO or ultraviolet light or 773 Kelvin, any one of this condition, then halogenation will be next to doubly bonded carbon atom. This is very important, because whenever complete the reaction type questions are asked, or even the convergent type questions, then you have to remember this condition, that if chlorine or bromine, it is treated with alkene in presence of ultraviolet light or HNO or sunlight or 773 Kelvin, then the halogenation will be next to doubly bonded carbon atom. Chlorine or bromine, if it is treated with any benzene ring in presence of anhydrous aluminum chloride, halogenation of benzene ring will take place. This will be studying again in the topic haloarene. Now electrophilic substitution reaction is the next method, and as I have already told you, it is especially for the preparation of haloarenes, and therefore right now I am skipping it because in this video I am going to totally focus on haloalkanes. So I will move to next one, halogen exchange method. In that first one, any haloalkanes, here a halogen can be either chlorine or bromine. Halogen can be either chlorine or bromine. When treated with sodium iodide in presence of diacetone, we get iodoalkane and sodium halide. So I will say this method is basically for the preparation of iodide, and this is a name reaction, Finkelstein. I have taken a simple example. Chloroethane when treated with sodium iodide in presence of diacetone will get iodoethane and sodium chloride. Now why we are using diacetone? Diacetone will act as a solvent in which sodium chloride will precipitate out, and therefore sodium chloride will be removed from the byproduct. As a result, according to Le Chatelier principle, the reaction will move in forward reaction, thus facilitating the reaction, and therefore diacetone is used. Till now, again and again I have told you that all these reactions are not applicable for fluorides. For fluorides we have to use some special methods. So this is one of them. Any haloalkane is treated with metal fluoride, either silver fluoride or mercury fluoride, then we get fluoroalkane along with AgCl, and this is your next name reaction, Schwarz reaction. Till now I have told you at least 5 to 7 name reactions. Now when you are studying, sit with a pen and copy, and all name reactions you start writing at one place, so that by year end you will have all the name reactions together, and it will help you in revision. So this is the last method, from silver salt of carboxylic acid. This is specially used for bromides. Silver salt of carboxylic acid, when it is treated with bromine in presence of non-polar reagent, we get bromoalkane along with the byproduct CO2 and silver bromide. This is a descent of series That means one carbon atom will be less in the product side as compared to that of reagent side. This carbon will be evolved in form of CO2. This is also named reaction Hunsdaecker. Okay, so right now I have told you Finkelstein, Schwarz, Hunsdaecker, and previously I have told you Darwin process, Groves process, and all other. So keep on writing all these named reactions at one place. This was all about preparation of haloalkanes. Now we'll move to the next topic, that is physical properties. So moving on to physical properties, as I have told you, in physical properties generally we discuss about water solubility, boiling point, density, symmetry, so on. But in case of haloalkanes, to understand water solubility, first of all we must understand the nature of carbon halogen bond. Now we have seen halogen can be attached to carbon when it is either sp3 hybridized or whether it is sp2 hybridized. Now whether halogen is attached to sp3 hybridized carbon or sp2 hybridized carbon, in both the cases carbon and hydrogen bond will be polar in nature due to difference in electronegativities. Okay. Now when halogen is attached to sp3 hybridized carbon atom, comparatively it will have more bond length. And when halogen is attached to sp2 hybridized carbon atom, comparatively have shorter bond length. That means whenever halogen is attached to doubly bonded carbon atom, whether in case of haloalkanes or whether in case of haloarenes, in that case the cleavage of carbon halogen bond is difficult. Okay, so second point is water solubility. We know that water being a polar solvent, all polar solutes are soluble in water, but haloalkanes are exceptions. Haloalkanes, although polar in nature, but they are immiscible in water. This is very important give reason question. Many a times it has been asked in board exams that why haloalkanes are immiscible in water, although carbon halogen bond is polar in nature. Now generally speaking, whenever we talk about water solubility, we say that if the given solute can form hydrogen bonding with water, then it will be water soluble. If it cannot form hydrogen bonding with water, it cannot form, it will not be soluble. But we can have one more reason for haloalkanes. Now when haloalkanes are dissolved in water, a large amount of energy is required to break carbon halogen bond because there is a great difference in electronegativity. Comparatively less energy is released when the new interactions are set up between haloalkane and water. As a result, haloalkanes are immiscible in water. But you can give a simpler reason also, that haloalkanes cannot form hydrogen bond with water. Moving on to boiling point. Boiling point, there are two cases. First is molecular mass. As the molecular mass increases, we have studied in 11th class that magnitude of van der Waals force increases and therefore boiling point also increases. In other words, I can say molecular mass is directly proportional to boiling point. For example, iodoethane will have largest molecular mass compared to all halogen derivatives of ethane, and therefore its boiling point will be highest as compared to bromoethane, as compared to chloroethane, or as compared to fluoroethane. The next factor which will affect boiling point is branching. In 11th class we have studied as the branching increases, boiling point decreases. They are inversely proportional to each other. For example, in this given one, bromopentane will have highest boiling point as compared to 2,2-dimethyl bromopropane, because maximum branching in this case. Maximum branching, therefore it takes the shape of sphere. This you have already studied in 11th class. As I have told at the starting of this video, this can be asked as give reason question, arranging the order type question. You will be asked to arrange them either in increasing order or decreasing order of boiling point. The last one is density. In density also there are two factors. As the number of carbon atom increases, density increases. Again, I can say these are directly proportional to each other. For example, iodomethane will be least denser as compared to iodopropane. The second factor is atomic mass of halogen. Atomic mass of halogen is directly proportional to density. That means as the atomic mass of halogen increases, density also increases, and therefore need not to say that iodomethane will be most dense as compared to fluoromethane, as the atomic mass of iodine is the largest one. Here I would like to introduce one more thing, that CF bond is highly polar in nature, because we know that fluorine is maximum electronegative, and comparatively carbon iodine bond is less polar in nature, because we know electronegativity decreases down the group. So we will take a break here. In our next video, we'll be discussing about the chemical properties of haloalkanes. Thanks for watching. Have a nice day.